Okay, there we go. It's recording now. All right. So, so we talked about this yesterday a little bit. A saturated solution is a solution where the solvent has dissolved the maximum amount of solute that it can contain at a certain temperature, right? So it has the maximum amount of solute. For example, let's say sugar in water, salt in water, or whatever. So it has taken in maximum amount of solute, and then it is called, or it is said to be at equilibrium because the amount of solute that is going into the solution is equivalent to the amount of solute that is being crystallized or being precipitated. All right. So this is something which I want you to remember. A solution is at equilibrium when it is saturated. So you should remember this, because a lot of problems, a lot of word problems, they give you this kind of a sentence saying that a certain amount of solute is dissolved in a solution which is saturated, which means they're talking about the equilibrium point. Okay, the solution is at is considered to be at equilibrium when it is saturated. So this is what the picture looks like. If you try to draw a picture trying to show rather what's happening in a saturated solution, here you see the amount of solutes going into the solution and the amount of solutes coming out of the solution. They are at the same rate. Okay, so we talked about this yesterday a little bit. So the solubility product, so we previously learned about KCs and KP. So now there's a new one called KSP, which is equilibrium constant or solubility product constant. Okay, so it tells you the amount of solute that can be dissolved in a given amount of solution, okay, depending on the solubility product constant. So, and for ionic compounds, okay, this is equal to the equilibrium constant. Whenever we're talking about ionic compounds, the KSP value is equal to K equilibrium value. All right. So, and then how do we calculate KSP? So KSP is calculated by taking the products over the reactants. So just like KP or KC, or for any equilibrium constant, it's always the products over the reactants. But one thing to remember here is that whenever we're talking about solubility, in almost every single case, our reactants will be solids because we're talking about solubility. There might be some cases where it may not be solid, but most likely in most of the problems you'll see that the reactants are mostly solids. So that's why KSP value in these two cases, which is CaCO3 and PbCl2, KSP is just the product of the concentration of the two products here, right? Because CaCO3 is solid, so we don't use solids and liquids in our reaction. So CaCO3 is solid, so we don't need to worry about that. So there is no denominator whenever we are calculating the KSP values. And PbCl2, same thing. Now, okay. Oops. We talked about this as well yesterday. The solubility rules you need to know for AP chemistry is all salts, okay, containing sodium ions, potassium ions, and ammonium ions these are the 4 positive ions or cations, and NO3 minus ions, nitrate ions. These 4 ions, whenever you have these 4 ions in your compound, that particular compound is always completely soluble in water. They are soluble in water, okay? So how will you know whether a particular product is soluble or highly soluble or less soluble? For that, you need to look at the KSP values. So the higher the KSP values, the more soluble a particular product is. Okay, give me 1 second. I need to move something off my slides here, which is blocking. So in this case, what is shown here is NaCl solid and Na plus and Cl minus. So because the presence of NaCl or Na ion, this is completely soluble, okay? Now, I think I asked you this question yesterday. So which compound is least soluble in water at 298 Kelvin? So we look at, I think Helen answered this yesterday. So calcium carbonate or lead chloride. So if you want to tell which is less soluble, you need to look at the KSP values, and the higher the value, the more soluble it is. So they are asking here for least solubility. So 8.7 times 10 raised to minus 9 is obviously much, much lower than 1.6 times 10 raised to minus 5. So CaCO3 is less soluble compared to lead chloride in water. Okay, so answer is CaCO3 as it has a smaller KSP value. So this is something you need to remember. The KSP value gives you the ability of a particular substance to dissolve in water. The higher, the better solubility it has. Okay, everyone? Yes, Journey.
So you know how like when we were doing the concentration, like CD over AB, or like whatever way it was,
Yeah.
will you be given the values for like Ca2 plus and Ca3?
Oh yeah. So yeah, when you for here they already solved for you.
Yeah.
But in the problems, we will do some problems like that. They will give it to you, or you will figure it out using the same ICE tables that we did before. So most likely they will give you some values and you will use them to resolve for the rest of the values, okay? So yeah, here they didn't give you anything, they just gave you the answer. It's just for you to compare those two, that's all, okay? Here you cannot calculate Ca, the values of individual things because they didn't give you anything else, okay? Make sense, Journey, for this problem?
Yes.
Okay. All right. So now let's look at this particular example. It says lead chloride. So whenever lead chloride is dissolved in water, you will have lead ions, Pb2 plus, and chlorine ions, 2L, or chloride ions, I should say, Cl minus. So the solubility is considered as the maximum molar concentration of formula units that dissolve at a given temperature. So whenever we're talking about solubility, it is the maximum molar concentration, okay? So again, here you see that we are slowly talking about concentration. So solubility of any substance is given as the maximum molar concentration that can go into a solution at that particular temperature. So at 25 degrees Celsius, sometimes there will be 1 mole of solution that can, one mole of the substance that can go into dissolution, into the solution. And for a different substance at the same temperature, it can be 2.5 molar. So every substance has a different level of solubility. And what do they mean by solubility? It just means that the maximum amount of concentration that can go into solution at a particular temperature. Everyone clear on that?
Why is it a 1/2? Why is it not a 2 in front of Cl?
I'll tell you why is it 2. Why is it 1/2? So for here, for every 1 mole of PbCl2, so they are talking about solubility of PbCl2, right? Correct? So how many? So for every 1 mole of PbCl2 that dissolves, 1 mole of lead ions and 2 moles of Cl minus ions enter the solution. Correct? So solubility of PbCl2 is, so how many moles do we have of PbCl2? There's 1, correct? And then Pb2 plus is also 1. So we're talking about 1, we're talking about the solubility of PbCl2, which is 1 mole. So how many ions of Pb2 plus are being produced? 1 mole. So here, this is equal, because they're both 1 mole, they are both equal. So this is equal to 1 mole of Pb2 plus ions. But in the reaction, how many moles of chlorine are being produced? 2 moles of chlorine are being produced. So to equate that to this equation, you have to subtract, or sorry, divide that by 2. So that's why it's half Cl2. Remember, in our equation, in our concentration equation, when we have these coefficients, they normally go to the square, right? They go up to the exponent. So here, they are trying to equate this to PbCl2. So 1 mole of PbCl2, the solubility of this will be same as 1 mole of lead ions, because that will release lead ions, and also will be equal to half of the Cl minus concentrations, because normally PbCl2 will release the 2 moles of Cl minus ions. So that's why it is half. Okay. So, and again, as I said before, at equilibrium, this solution is saturated. Now, how do we calculate solubility products? So let's do this quick example. So first, it's given that the solubility product constant for lead fluoride is 3.6 times 10 raised to minus 8 at 25 degrees Celsius. Now, first write the balanced equation. Can you guys try it? What is the balanced equation of lead fluoride when it is dissolved in water? If write it, and I can see you all now, so you can show it to me on a piece of paper or something. Or let me try this whiteboard. I've been meaning to do that. All right. Helen, do you have it?
Yes.
Show me.
I show you? How to show you?
Oh, I thought you have a piece of paper that you can put it on your videos.
Oh, I write in OneNote.
Oh, OneNote. Okay, can you just tell me?
Yes. Is it PbF2?
Mm-hmm.
You know, the arrow thing?
Mm-hmm.
Created Pb plus 2,
Mm-hmm.
F2 minus 1.
And F minus 1, did you say?
Yeah, F2 minus 1.
F2 minus 1? Okay. There's a little problem in there. I'll show you. I don't know, maybe I heard you wrong. Let's see. Is this what you all get? Let's see. I'm going to write it down myself. How does a fluoride ion exist as? Chlorine, fluorine.
F2.
Are you
Isn't
sure?
it?
Ions.
Like flashing. Oh, no. 2F minus 1.
Yeah.
Yes, that one.
Take a look at that. Everyone got this? PbF2 is Pb plus 2 plus 2F minus. Right, Helen?
Right.
Got it?
Yeah.
Max, you got it? Yep. Someone asked for something, Johnny? Yep.
Your screen keeps flashing.
Is what?
Your screen keeps flashing, like it keeps going in and out, and then it like gets small for me, and then gets big, and then goes in and out.
Really? That's weird. Let me just pin myself, so maybe it will better, maybe. Let's see. I don't know why it is doing that, Johnny. Is it doing for everyone else like that?
No.
No? Okay. Let's.
Okay, wait. I'll leave and then come back.
Yeah, probably that's a good idea. So, okay. Now, can we write the equilibrium expression for that equation, everyone. So that's the equation. PbF2 will give you Pb2 plus 2F minus. Now let's write the KSP equilibrium expression. So KSP is equal to what? All right, so I'm assuming most of you have the answer. So KSP value would be Pb2 plus the concentration of that times the concentration of fluoride ions. So taken twice, I mean not twice, to the power of 2. So because we have 2F minus here. Got it, everyone? Now, based on that, can you guys calculate the molar solubility? So you are given that the solubility product is given as 3.6 times 10 raised to minus 8 at 25 degrees Celsius. So KSP value is given to you. Now find the maximum molar concentrations of the ions in the solution and the molar solubility of the solution. So how will you do that? So I will show it to you because you probably know. So all you need to do is like the way we do X and 2X similarly. So S is the molar solubility. So S is given as, because it's Pb, so you can just put S there for molar solubility. And F is 2S, and because it is 2 moles, okay? And then because it's square here, so which goes up here. And then when you do the whole thing, 2S square and S will be 4S cube, because it will be 4S square times S, it will be 4S cube. So when you calculate the value of S, which is the molar solubility, that is given as 2.1 times 10 raised to minus 3. So these two values, S and 2S, they give you the amount of concentration of these ions that are soluble in this solution. So you have fluorine ions will be twice of this when you use 2 times S and square. So that will be the amount of fluorine ions that can go into the solution, whereas the amount of lead ions that can go into the solution will be S. So this is called as molar solubility. This is how we find the molar solubility, okay? Journey, are you back?
Yes.
Okay, good. Is it better?
Yes.
Okay, good. So make sure you have this in your notes somewhere. Make sure you make a note of all these. Can I move forward, people?
Yes.
Okay. All right. Now, this is S, and then, of course, as I said, for fluorine is twice of S. All right, so KSP, and I'm gonna leave it here for a little more time. So you have this 2S is the value of that. Okay. All right, so if, remember we talked about a reaction quotient, so it's same thing as what reaction quotient in terms of solubility product. If QSP is equal to KSP, then the system is at equilibrium. So if the reaction quotient of the solubility product is equal to the equilibrium of the solubility product, then the system is at equilibrium. If QSP is equal to KSP, the system is at equilibrium. It is saturated because, as I said, all saturated solutions are at equilibrium with solid and aqueous species. So there is both equal rate of conversion going on there. If QSP is greater than KSP, then a precipitate will form because the reaction will proceed to the left until the system reaches equilibrium. So if in a question they ask you based on whatever data they give you, if they ask you, will there be a precipitate forming in this reaction, what you need to do is you need to calculate the QSP values that at what they have given you and compare that to the equilibrium. So QSP, you use the initial concentrations, and for KSP, you use the equilibrium concentrations, and then you compare those two, and then you will be able to tell whether there's a precipitate forming in that particular reaction or not. And if there is other way around, if QSP values are smaller than KSP value, then no precipitate will be formed and all the ions will remain in the solution because the solution is unsaturated. All right, so based on this, let's do a couple of problems. Let's find the KSP value for a saturated solution of PbCl2 if the concentration of Cl minus is found to be 0.0325 molars. So the first question is asking you to find the KSP value for a saturated solution, which means the solution is at equilibrium already, right, of PbCl2. If the concentration of Cl minus ions is found to be 0.0325 molars. So how would you do that? First of all, make sure you write the correct equation. So PbCl2 will give you Pb2 plus ions plus 2 Cl minus ions. Now, let's write the equation for the KSP, so which is Pb2 plus and Cl minus. So they are asking us to find the KSP value, but they just gave us the value of one of them, right? So we use this problem from before, this equation from before, so S times 2S square, and because the value of S is given to you, which happens to be, the value of Cl is given to you, which happens to be 2S, you can safely assume if value of CS, the concentration of Cl minus is 0.0325, which is 2S, S is half of that, obviously, right? 2S and S. So you can assume that this is 0.5 times 0.0325, and then you solve for that. You will get the value of KSP. Everyone clear so far? Yeah. So make sure you quickly make a note of this, and then we will go further. Okay, this is how we solve such problems. Again, if they give you just one of them, you can use the balanced equation to see what these values will be. So S, and because it's a Cl, 2Cl minus, so it will be 2S square. Okay. And for the second problem, I don't know, the second problem is, will a precipitate of PbCl2 form when 200 mils of NaCl is mixed with 100 mils of lead nitrate? Assume that the temperature of the resulting solution is the same as that from part A. So will a precipitate of PbCl2 form when 200 mils of NaCl, of this many molars of NaCl, is mixed with 100 mils of this many molars of lead nitrate? Assume that the temperature of a resulting solution is the same as that from part A. So we will solve that problem as well. First, find the concentration of Cl minus. So it is given you as number of moles, right? So you convert that into this particular total number of moles of Cl minus that are present in there in the total solution. And then you find the concentration of the Cl minus ions, so which is number of moles over volume, that will give you the molarity of Cl minus ions. I will wait for a minute so you can make a note of this. So the first step is to find the total number of moles in that given amount of solution for Cl minus, and then you'll figure out the molarity, the concentration of Cl minus, which is N over the volume, total volume, okay, because they're adding 200 mils and then 100 mils. So the total volume down here will be, convert that into liters, so which will be 0.2 liters and 0.1 liter. That's the total volume now, okay? Now, I hope I can move further. Step 2, similarly, you'll find the concentration of lead ions. So same idea, but instead of chlorine, you will put down the lead ions there, okay? And you will find the concentration of lead ions. Okay. And if you don't get enough time to record or write this down, this is being recorded, so I will post on your Google Classroom as well, so it should be there. So you find, similarly, you'll find the concentration of lead ions, and then you'll find the Q value for lead chloride. So, which is Q is the concentration of Pb, lead ions, times Cl2 minus ions, so which you got here. So now, when you multiply that, you get the value of Q. So now KSP value you found out from before, right? And then you compare the Q and KSP. If Q is less than KSP, that will be soluble or insoluble. The solution is unsaturated, so no precipitate will form. So when Q value is less than the KSP value, no precipitate will form. Okay, everyone? So this is how we solve these problems. So now for the next 10 minutes, this is, so I hope everyone understood this stuff. Okay. The next one, which is one of the important topics, it's called solubility and the common ion effect. So here, if you look at this slide here, we have PbCl2, okay, and which dissolves to form lead ions and chlorine ions. Now, if to this reaction, if I add NaCl or KCl or some other compound which has a common ion, whenever I say a common ion, when this dissolves, it should be able to produce Na plus and Cl minus. So now we have these two Cl minus common ions, okay? So whenever this happens, whenever you add a salt or another compound to this reaction, and this addition creates a common ion with the actual original reaction, because you are kind of adding chlorine towards the right side of the equation, right? So which means you're increasing the concentration of chlorine ions. Now, what do you think will happen whenever I'm increasing this chlorine ions here? What do you think will happen? Will the reaction still keep producing more chlorine ions, or will it move the other way? Anyone? Will move towards the other way, because this addition resulted in this common ion, so which is adding to the concentration of this original chlorine ions. Now that kind of ruins the balance of this equation. So now instead of this being at equilibrium, the reaction will shift towards this side, causing it to form more precipitate than it being more in the dissolved form. Okay, so in this case, chlorine ion is the common ion that causes the equilibrium in the first reaction to shift, okay? So, well, before I go to that example, I want us to solve. I'm going to share another document and we will figure out how to solve this together. So I'm going to stop sharing this PowerPoint for now and I will share something else. Okay. And where is the share thing? All right. Can you see this Word document, everyone? Yeah? Yes? Yes? No?
Yes.
Okay. All right. So can we solve for this? I want you to make a note of this problem, okay? So calculate the molar solubility of PbF2 in, first is 0.5 molars NaF, okay? And then B is saturated solution of lead fluoride. And C is what effect does presence of common ions such as F minus have on the molar solubility of PbF2. So let's try to, so what is the, can you first write the equation for this? What is PbF, what will PbF2, we already did this, right? So I think we did a similar one, so I will just write it for you. I'm gonna plus 2. Of course, this is in the, okay, well, whatever. You guys get it, right? So plus 2F minus. So you guys get the idea. It's like all weird, but it's Pb plus 2 plus 2F minus, correct? So what is the initial initial concentration of, let's say, what is PbF2? So it says calculate the molar solubility of PbF2 in 0.5 molars of NaF, okay? And what effect does the presence of common ions such as F have on the molar solubility of PbF2? So what do you think? What else is missing in this? Is there something that is missing that you need to figure out this problem? Yeah?
I'm confused where sodium came in.
Yeah, we are adding it. So we are adding extra sodium to it. So this is a salt which I'm adding to it. So remember, so so make sure you all have this problem. Write down this problem. This is your homework. So you all have this problem, okay? And then we will talk about it. So NaF is something which I was adding. So that's what a common ion effect is. So just make sure you all have this, and we will work on it on your own time because we are running out of time right now. So I will just go back to that PowerPoint before. And so Max, to answer your question, where did that NaF come from? The NaF came from the fact that we are actually adding NaF to the solution. So that's why, so like just like this here, you see PbCl2, that was our initial salt that we are talking about. And then I'm adding some NaCl. Similarly, in that problem, I added some sodium fluoride when it was PbF2. So to create this common ion effect. All right, so now, got it?
Yeah.
Okay, so this is an example. I will post that on the Word document on your portal or your Google Classroom, so we can solve that as a homework. So find Ba2 plus and as the concentration of Ba2 plus and concentration of SO42 minus after 0.2 grams of barium nitrate are added to a 400 ml of saturated solution of barium sulfate. So you have barium sulfate, and then you're adding barium nitrate to it, and the equilibrium is established. assume that the volume remains the same and the final temperature is 25 degrees Celsius. Now, and KSP value is of barium sulfate is given as 1.1 times 10 raised to minus 10. So find the moles of barium in the original concentration. So how will you do that? So KSP is obviously given as Ba2 plus SO4 2 minus. So KSP is S square because it's 2 minus. So S is, because KSP value is given as 1.1 times 10 raised to 10. So S value is the square root of that. And so the initial concentration, the solubility product, or the molar solubility of both barium and sulfate is 1 times 10 raised to minus 5, which is the square root of this. All right. And now we can find the number of moles of barium by using that formula over 1 liter, because the initial, the volume, the total volume is 1 liter. Okay. And then find the number of moles that barium was added, and then you will find that. And then we can find the concentration of barium ion using the same formula. So barium ions increase from this to this. Okay, so we will go over this in detail because running out of time, I cannot go in detail, but I want you to, tomorrow we will start over at this problem and go in detail, but I want you to look up common ion effect, read up on this, and try to solve that problem, the word problem, using ICE tables. So that will help you a lot to solve for that. And I will post the whole, the entire problem on your Google Classroom, but I want you to give it a shot. All right, everyone? So I'll see you tomorrow. I think tomorrow is F day, right? So we will have a lot more time to solve some more problems based on this common ion effect, because it's a very important concept. And it's actually simple once you understand this. It is very, very simple. And one more thing I want to tell you is that I was told recently, I got an email saying that there are some free review classes from AP board, the college board. So you can go to their website and there are some classes that they're offering in every subject that you're taking, like any, not just AP Chem, but every subject. So you can look up their schedule and you can join those classes as well if you have time. All right? Everyone okay with that? Everyone? If you have any questions, email me, but we will revisit this solubility KSP problems tomorrow, the common ion effect problem, and hopefully we will try to finish it by this Friday, this chapter, and then I'll send you some material for spring break and you're going to work on it. And I'm offering my help. I will be online even during spring break, at least for a couple of hours every day. So I will open a meeting for you guys to join in if you want. And you're welcome to join in if you want to ask any questions, all right? Over the spring break too.
Okay.
All right, guys, have fun. I'll
Have a
talk to you
great rest
tomorrow.
of your day.
You too. Bye.
Bye.